Is this a median, an angle bisector, or an altitude? We just did that in our warm-up. Which one is this one? Altitude, yeah, good. So this is an altitude. So remember, an altitude is a line that connects the base, a vertex to its base. At what kind of angle does it connect? At a 90-degree angle. Good. You guys are so awake today. We got this.
Remember, you hear altitude a lot when you think about how tall or mountain is or something. And usually, when you measure the height of something, it goes in a straight line at 90 degrees from the base to the highest point.
All right, so in this example here, we have triangle ABC is similar to triangle FGH. Did you need a glue in, Anthony? All right, so what is our altitudes in these two triangles and these top ones? Good, FJ and so FJ and what? AD. Good. So I can compare those, FJ over AD. And I can compare them to any of the sides. So I can compare those altitudes, even though it's not a side over a side. We can act like it's a side. It's one of those proportional parts. So I can pick any side I want from the next part. We started with FJ, so I'm going to have to pick a side from this bottom triangle. What side do we want to pick? It doesn't matter. HG, the bottom. Let's not do the base. So I'll pick a different one. Let's do HF. We do HF. Okay, sorry. All right, HF. I'm sorry. I hate it when I do that. Sometimes I'm like, let's pick one, and then I change my answer. Because it just doesn't have to be the base. It doesn't have to be the 90 degrees. So I just want to show that. Okay, so HF. And HF are my outside letters here, HF. So I just want to double check that that works with the second triangle here. What would match our outside letters? AC. But this could have been any of the sides. So today is just about realizing which ones we can have relationships with and which ones we can create. And here it works with altitudes. All right, our next one. What kind of segment do we have in the middle of those triangles this time in that center? Is that a median or an angle bisector? In our middle example here. Yeah, an angle bisector. Good, it cuts that angle in half. So an angle bisector which cuts an angle in the middle. Or cuts an angle in two congruent parts. So it cuts an angle in the middle, making two congruent parts. All right, so in this one, if I have triangle QRS, good morning, Houston. And then do you have your notes? Okay. We have triangle QRS is similar to triangle KLM. Said that really weird, KLM. So cuts an angle in the middle, making two congruent parts. Triangle QRS is similar, did I say congruent? Is similar to triangle KLM. All right, so let's start by comparing our angle bisectors. Which two parts are angle bisectors in this one? Good, LP and RT. So we can compare those angle bisectors, LP over RT, or we could have done RT over LP, that's fine. And then we can compare that to any of our sides. So if I pick LM this time, what's going to go with that LM? RS. Good, and if we just look at it, we could see that, but if I'm not sure, we always look back at that similarity statement. LM is the last two letters, so it should go with RS, the last two letters. Should be LM on top or on bottom? Why in the numerator? That's right. Why did we put LM in the top part, the numerator? Remember, it has to match with that other one. So LM matches with LP. It comes from that same triangle. Okay, so again, this could have been any side. It doesn't have to be the one right next to it on the right side. We could have used any side. All right, two more. In our third one here, so if you joined us late, we're on this third one, you can just jump down to that third part, and then you can fill in those rest later. What kind of segment do we have here in the middle there? Is that a altitude, angle bisector, or median? Good, it's a median. It goes from the midpoint to the outside, so these ones are medians. And a median connects the midpoint of a side to the opposite angle, or you could say the opposite vertex. So it connects the midpoint of a side to the opposite vertex. All right, so triangle ABC, in this case, is similar to triangle WXY. So if we know that those triangles are similar to start with, then we can set up those proportions. That's the important part, is that they have to be similar first. It doesn't work with just any two random triangles. It has to be two triangles that are similar. And then we can set up those proportions. Ugh. All right, so what are two medians that we have? WX is a side. What's the median? Good, Z to Y. Because Z is that midpoint. We see it's congruent on both sides. And what's our other median? DC. That's really interesting, Ephra. You always start with the right one. I always start with the left one. It's kind of interesting how our brains work, just a little differently. So I'm going to start with that CD this time, just to switch it up a little bit. Normally I switch it up and go the other way, but we've already been doing that way. CD over ZY. And then we can compare it to any side we want, as long as we have another side somewhere labeled. So what other side do you guys want to compare that to? BC. Okay, BC goes with XY. But again, it could really be any side that goes together that has a relationship. It doesn't have to be BC. We could have picked AC. We could have picked AB, as long as we have any of those sides. All right, last one. This one's a little bit different. What do we have in this one? An altitude, an angle bisector, or a median? Good, an angle bisector. And instead of having two separate triangles, how many triangles does this one actually start off with? It technically actually only starts off with one triangle, JKL. So it's starting off with this JKL and then having an angle bisector. So this is a theorem, triangle angle bisector theorem. Which just says if I have an angle bisector of a triangle, and I only have one triangle, I don't know why I'm writing so weird, sorry. My spacing is really off today. If I have an angle bisector, that means I now have proportional parts. So as we take a look at this, what part is the angle bisector? JM. And what angle is JM bisecting? Good, nice correction there. KJL. So we started off with that angle KJL. And JM bisects that. So I'm going to write that out as a part of our theorem here, is that JM bisects angle KJL. And really what this theorem says is it now creates these two parts that based on our similarity statements, it really creates two similar triangles now. Instead of just having one triangle, it splits into two triangles that are similar. And that's where this theorem comes from. So now if I look at my proportional parts, I'm going to start with those two sides I already named. So J to K, I would compare that to, what's the side that goes with JK? JL. I'm going to take that back. They don't create similar triangles. Ignore what I just said about that. I was trying to make it meaningful, and then it just ended up being lies. Lies. All right, and then if I look at those two triangles, what I can look at is those two parts at KM and ML. So I kind of think like across go together, and then like the top parts go together, and the bottom parts go together. All right, because we've been doing so many ratios and setting up ratios and solving ratios and proportions and things like that, I don't actually have ones today where we're solving them in the notes. So if you're still confused on how to set those up when you actually have numbers, please make sure you're asking today. Okay? You're going to have in your practice today, there's going to be problems where you have those numbers that you're setting up, and then you are going to be solving them, finding those missing parts. Okay? So it looks a lot like the last two lessons, two homeworks. Should be pretty straightforward. If you need help on any of the homeworks, let us know. I did update the gradebook last night.